Mr. Carlson here, and we're going to begin our notes on Chapter 10, which has to do with this concept called the mole. Before we get into looking at what the mole is, let's first talk about the differences between when we use terms like atoms, molecules, and formula units, and the differences between those things. So let's first imagine that we have a piece of aluminum foil, and we keep cutting that piece of aluminum into smaller and smaller pieces. At what point would we get to the smallest piece of aluminum that still has properties of aluminum? And that we've already talked about is an atom. So an atom would be the smallest piece, or an aluminum atom would be the smallest piece of aluminum that we could get that would still have the properties of aluminum. And if we were to break down that atom further, we would no longer have aluminum, right? So therefore, the smallest particle of any element from the periodic table is called an atom. So if we're dealing with elements, then that means we are dealing with atoms. But what about the smallest particle of, let's say, a compound like water? The smallest particle of a compound like water that still retains the properties of water would not be an atom, okay? We don't have water atoms, right? Because if we were to take a molecule of water and break it down to its components of just hydrogen and just oxygen, which we could do, well, then we'd no longer have water. We'd have hydrogen gas and oxygen gas separate from each other. So before we can break it apart into its atoms and still have the same properties, that means we are dealing with something called molecules. Remember that we only use the term molecules when we are dealing with nonmetals that are bonded with other nonmetals. So in other words, when it is a covalent substance. So covalent substances, remember, that'd be things that like maybe N2O or P2O5, whoops, 5 would be down here, or H2O. They are things that have only nonmetals. Nitrogen and oxygen, nonmetals. Phosphorus and oxygen, nonmetals. Hydrogen, oxygen, all nonmetals. So those are covalent, and when we're working with those things, we refer to those as molecules. So if I had a beaker of water right here, that beaker of water, if we were to zoom in on it, is made up of individual H2O molecules. And that would be the smallest part of water, would be those H2O molecules, right? So that's what we're talking about when we deal with covalent substances, which are molecules. What about if we deal with something that's not covalent, like table salt? Table salt, which is NaCl, that has right there a metallic element, or a metal. We said that anything that has a metal in it is ionic, not covalent. And so for these, they are not made up of molecules. So if we were to zoom in on a piece of salt, we wouldn't see, like with the water here, where we've got these kind of individual water molecules that are interacting with each other. So like in a thing of water here, we'd have these water molecules, and they're kind of moving around and interacting with each other. That's not the case when we have something that is ionic. When something is ionic, what we get are, and we've talked about this before, we get these alternating ions, these alternating charges that are in this repeating pattern, or this repeating structure, which we called a crystal lattice. So for table salt, it would look something like this if we were to zoom in on it at the atomic level. We get these alternating positive and negative charges, which are kind of stuck together, which make this nice, neat pattern. And that's what we would see with an ionic compound. So this kind of crystal lattice structure. And so we really don't have like individual molecules of salt. What we have is this really big crystal structure of repeating ions. And so we can't use the term molecules for this. We use the term formula units. And so a formula unit would be the smallest particle of an ionic compound that retains the properties of that compound. And so when we're dealing with the smallest particle of a substance, it depends on the type of substance that we're talking about. So let's say we go on to this next page here. Let's say we look at these examples here. We've got three different things. We've got this compound called magnesium chloride, this compound of dinitrogen monoxide, and then sodium by itself. And so in each case, we'd be dealing with something different. For the element alone, that would be something like sodium. The type of representative particle would be atoms. So if I have sodium by itself, I'm dealing with sodium atoms that make that up. For the covalent compound, that would be N2O. We know that it's covalent because it's made up of only nonmetals. And so if I'm dealing with this dinitrogen monoxide, what I really am dealing with is dinitrogen monoxide molecules. And then for the ionic one, where it's a metal bonded to a nonmetal, that's that MgCl2, which is magnesium chloride. And if I'm dealing with magnesium chloride, that means I'm dealing with formula units of magnesium chloride. And so we should be able to tell what we're dealing with, atoms, molecules, or formula units, just based on what the formula is. And so remember, as soon as I see a metal at the front, I know it's ionic. And if I know it's ionic, I know it's formula units. I'm just going to abbreviate it, FU, formula units. For letter B, SO2, only nonmetals, so that's going to be molecules. CF4, again, only nonmetals. Molecules is what we're dealing with there. Mg by itself, if I have something that's all alone, not bonded to anything, that means I'm dealing with atoms. So that would be made up of magnesium atoms. Se by itself, same thing, atoms. CaBr2, I see a metal at the start, that means it's ionic, so formula units. NaNO3, same thing, metal in the start, so formula units. And then Br2, so we do have two things bonded together to make a molecule, but remember we talked about those. That's a diatomic molecule. It's made up of only one type of atom, and so that would be atoms for that one. But I suppose we could make the argument for molecules as well in that case, since it's made up of two things bonded together to make a molecule, a diatomic molecule. But we could also say atoms in the sense that it's only one type of atom in there. So now that we've determined the type of particle that we're going to use, how do we count these particles? So how do we count how many atoms that there are or how many molecules that there are in a substance? It's kind of impossible to count them directly. We can't just look at a substance and count out how many atoms it has. And so chemists use a counting unit called the mole. When we abbreviate this, when we write it out, for some reason we drop off that E, and so usually when we see it, it's just MOL. And it is defined as the number of carbon atoms in exactly 12 grams of carbon. Carbon-12, the isotope carbon-12. So if you have 12 grams, if you weighed out 12 grams of carbon-12, you'd have exactly 1 mole. And a mole of anything contains 6.022 times 10 to the positive 22nd power. This number is often referred to as Avogadro's number. Sometimes it's called that because, whoops, not numbers, just number. It's in honor of this scientist, Amedeo Avogadro, who determined the concept of 1 mole of a gas. So if you have a mole, you have an Avogadro's number of particles, which is this amount right here. Actually, it's not 22, it's 23. Sorry about that. I got stuck on 22 because of this, but it's 6. Let me fix that. It's going to bother me. So 6. Oh no, now I can't write there, I think. I 6.022 times 10 to the 23rd power of representative particles, which is a really, really big number. So how can we use that number to figure out how many moles or how many individual particles that we have? It's the same way. So when we use this mole, it's kind of the same as like if we were to use this right here. 1 dozen is equal to 12. So you know that if you have a dozen of anything, you have 12. Whether it's roses, eggs, donuts, if I say that I have a dozen of them, well, that means that I have 12 of them. It's the same concept with a mole. If I say that I've got a mole of particles, I have 6.02 times 10 to the 23rd power. So for example, let's say that you have 8.5 dozen roses. How many roses do you have? Now this is a very simple problem right here. I know it's simple, but I'm going to show you a setup that I want you to follow. Even though I know it seems simple at first, we want to learn how to do this setup now because problems are going to get much more complicated down the road. So let's say we start with 8.5 dozen roses. And we want to figure out how many individual roses that is. We're going to use this right here as a conversion factor. And a conversion factor is a way for us to convert between different units. So right now my unit is dozen. And I want to convert that to individual roses. So the way that we do that was we're going to multiply this by our relationship here. There is 1 dozen for every 12 roses. And so the way to remember this is that when I'm multiplying something by a conversion factor and I want to convert this unit into something else, I need to put the unit that I want to convert into, that needs to go on the top of this because I'm going to write this like a fraction right here using these two numbers. And so I could write this as 1 dozen over 12 roses, or I could write it like this, 12 roses over 1 dozen. Both are saying the same thing, and so I can use them equally, but it's going to depend on what I'm trying to convert into. So I'm trying to convert from dozens into individual roses. So I'm going to use this conversion factor right here, and I'm going to write it like this, 12 roses for every 1 dozen. And the reason why I want to set it up like that, if I look at just the units here that we're using, dozen and roses, and if I think about the fact that this has got an imaginary 1, this is all numbers like that are going to be over this imaginary 1 here. And if I were to take this 8.5 dozen and I multiply it by 12 over 1, when I do that, anytime we have units that are being divided by each other, so this dozen would be on top and it would be divided by a dozen. Whenever I've got that, or if I think about it like them being diagonal from each other like this, they are always, when I have the same units like that, they're going to cancel out. So when I divide dozen by dozen, those units are going to go away, leaving me with the units that I'm interested in, which is roses. And so that means to solve this problem, I have to take 8.5 times 12 divided by 1 to give me my answer in the end. And if we were to crunch the numbers on that, 8.5 times 12 is going to give me 102 roses. Now I know that that seems like a really long, complicated way. I'm sure you thought to yourself, well, I just know without setting this up, I know that I have to take 8.5 and multiply it by 12 to get my answer. I don't have to do all this unit canceling and set this up with a conversion factor. And I get that, trust me. But like I said before, we want to learn how to set up these simple problems like this first, using this process, because later on it's going to get a lot more complicated, and you want to know how to do this process now with the simple problems, because later on they're not going to be so simple. So you need to know how to use this process now with canceling out those units before it gets much more complicated. Now let's remember this as well. So if you have 1 mole of something, 1 mole of representative particles being atoms, molecules, formula units, if you have a mole of those, you have exactly 6.02 times 10 to the 23rd power. So if I have 1 mole of atoms, I have that number, 6.02 times 10 to the 23rd. Just like if I have a dozen of something, I have 12. So if I have a mole of molecules, then I have that many molecules, 6.02 times 10 to the 23rd. And if I'm working with formula units, like with an ionic substance, then if I have a mole of it, I have 6.02 times 10 to the 23rd formula units. So the thing to keep in mind is, if you see that you have a mole of something, this is the amount that you have. Whether you're working with atoms, molecules, formula units, we could be working with baseballs, eggs, it doesn't matter. If I have a mole of them, this is the amount that I have, okay? So let's look at doing a couple more examples here. So let's say that we have 5.1 moles of something. How many individual particles of that substance do we have? So let's try and set this one up just like we did in the previous one. 5.1 moles. And what we're going to do is we're going to multiply it just like we did with the dozen roses here. My conversion factor is that 1 mole is the same as 6.022 times 10 to the 23rd power. Or we'll say 6.022 times 10 to the 23rd individual particles. Just like we would have said individual roses. So if I have 5.1 moles and I want to convert that to individual particles, that means I want to have particles on the top right here of my conversion factor. So I'm going to put this number on the top and moles on the bottom. So it would be 6.022 times 10 to the 23rd particles over 1 mole. And so I know that if I want to convert from moles to particles, I have to multiply 5.1 by 6.022 times 10 to the 23rd and then divide it by 1. Which if I do that, 5.1 times this would give me 3.07 times 10 to the 24th power particles. Okay? Let's say that if we have 2 moles of water, which remember, water means we're dealing with molecules. How many molecules is that? Well, we're going to set this up just like we did up here. We are starting with 2.0 moles of water, and we want to convert that into particles. So we're using that same conversion factor. 6.022 times 10 to the 23rd particles for every 1 mole. And again, moles here is going to cancel out because they're diagonal from each other, leaving me with individual particles. So 2 times 6.02 times 10 to the 23rd is going to give me 1.2 times 10 to the 24th power of water molecules. Last 2. This time we're starting with individual particles. We have 3.71 times 10 to the 23rd representative particles, and now we want to know how many moles is that. So now it's like we're working backwards. So it's going to be set up very similar to those previous problems, but now we're going to have to flip that conversion factor around. So now I'm starting with 3.71 times 10 to the 23rd particles. Now we're going to do the same thing. We're going to multiply it by this conversion factor right here. But if I look, I'm trying to convert from particles now into moles is what I want to figure out. I want to figure out how many moles this amount is. So moles needs to be on top this time because that's what I want to convert into, and particles needs to be on the bottom. Because, remember, this is going to be diagonal, and I want that to cancel out this time to leave me with moles. So now it's going to be 1 mole on top, and that's 6.022 times 10 to the 23rd on the bottom. So now what my math is going to read, 3.71 times 10 to the 23rd times 1 divided by this. So really what I'm doing is I'm taking this number and dividing it by this one to get my answer. And that works out to be 0.616 moles. So if I had this many particles, I would have that many moles of that substance. Last one. We've got 2.2 times 10 to the 24 molecules of water. In fact, if you want, pause the video right now, try and set this one up on your own, and then we'll see if you got it right. So hopefully you paused it and tried to do this one on your own. So we've got 2.2 times 10 to the 24 molecules this time. And now we want to convert that to how many moles of water that would be. So just like up here, moles needs to be on top this time, and particles needs to be on the bottom. Particles. And so it's going to be 2.2 times 10 to the 24 divided by 6.02 times 10 to the 23rd. And for that, we end up with 3.65 moles. And that would be it for that one.